Hello, and welcome to our webinar on what is pH. In this course, we would like to explain the key concepts around pH as a chemical property. In this webinar, we will start by understanding the importance of pH in organic and inorganic environments with the help of examples of daily use. We will then understand the basic terminologies related to pH, followed by its measurement concepts. We've all heard the term pH at some point in time in various contexts. Whether it be with respect to the pH of acid rain due to environmental pollution, or pH of cosmetics, or the pH of beverages in the fermentation process like wine and beer. pH is an often measured parameter in quality control laboratories, across various industries. It is also used in the production environments, natural sciences, human and animal health care, cleaning and sanitation, and environmental monitoring of soil and water bodies. Having said that, not all are aware of the theory behind pH. This webinar aims to contribute to a better understanding of the nature of pH. It is dedicated to amateurs as well as to people who want to brush up on their knowledge about pH. The pH of an aqueous solution ranges between 0 to 14 units. This slide shows some common examples of daily use, bracketed within this range. Foodstuff like bread, meat, milk, dairy products, vegetables, and fruits belong to the acidic region of the scale. pH of the stomach, soil, and the acid rain also falls in the acidic region. Acids like sulfuric acid, hydrochloric acid, acetic acid, etc., are also in the acidic range. Egg white is an exception amongst the foodstuff as it falls around the alkaline pH range. One also finds the antacid, a promising medicine against acidity problems, in this range. Several household chemicals like sodium carbonate, also known as baking powder, or ammonia, used as a fertilizer, and caustic soda, fall in the alkaline region. Having seen the applications, we hope you understand the importance of pH as a property. Let us now go through some of the basic concepts of pH measurement. The hydronium concentration is expressed as pH. pH, that is, Pond's hydrogeny, is one of the most common explanations for the term pH in literature. Regardless of this historical ambiguity, from a mathematical point of view, pH is the negative logarithm of the activity of the hydronium ion. What does this mean? For those who are not familiar with logarithm, it is explained here by means of a very common example. 1 cent is equal to 0.01 euro. In exponential notation, this is 10 raised to minus 2 euros. The exponent of this number corresponds exactly to the logarithm, which is minus 2. From this, we now take the negative value. So, the negative logarithm of 0.01 euros is 2. We now move on to the tenfold value of 1 cent. 10 cent, which is equal to 0.1 euro or just 10 exponent minus 1 euro. The logarithm from this is yes, minus 1, and hence, the negative value is 1. What we see now is that a tenfold increase in money results in a decrease by 1 in the negative logarithmic notation. Try to imagine what happens if we play the same game again. The result is a bit surprising. The negative logarithm of 1 euro is 0. Did you get the same result? A further tenfold increase in money even leads to a negative value, which is now minus 1 for 10 euros. A millionaire thus comes to a fortune of minus 6, which does not seem very impressive, does it? As shown in the slide above, the logarithm is a useful mathematical measure to express a huge activity range with just a few digits. The graph line exhibits the activity of hydronium ions plotted against the pH. As we move right along the pH range, the activity of the H+ ion decreases from 1 mole per liter to 10 femtomole per liter. The latter value corresponds to an activity of 10 raised to minus 14 moles per liter, which is barely detectable for most other chemical substances. Before moving on to the presentation of the hydroxide ion, we want to stress again the most confusing feature of the pH. It can be summarized with a statement. Every increase of 1 pH unit corresponds to a tenfold decrease in H+ activity and vice versa. Next, let us learn what is autoprotolysis of water. Pure water contains dissociated H+ and OH ions, along with the undissociated water molecules. Both ions evolve from the autoprotolysis of water. What's all about this autoprotolysis? Obviously, the water molecule does not seem to be fully stable. Time and again, it happens that an H+ ion leaves its place at a water molecule to join a neighboring water molecule, thus building an H3O+ ion and an OH ion at once. These two ions are then rapidly separated and surrounded, individually, by a hydration shell of other water molecules and get thereby stabilized for a certain time. Nevertheless, the process is fast and fully reversible. Although the H+ ion in an aqueous solution, therefore, exists as H3O+ ion, its activity for the sake of convenience will be expressed as A of H+ throughout the course of the webinar. Coming back, its significance? In pure water, that is neutral pH, the activity of hydronium ions and hydroxide ions are equal to 10⁻⁻⁷ moles. In other words, there is only one hydronium ion and one hydroxide ion in about 500 million water molecules. So why is pH that important? The answer will be given in the coming slides. The activities of hydronium ions and hydroxide ions in water are always correlated to each other. This is fundamental in the understanding of pH, and universal for aqueous solutions. Its impact on H+ and OH activities is like that of a tilt lever, which acts over the whole pH range. Therefore, pH and pOH always add up to 14 under standard pressure and temperature conditions. And the activities of hydronium and hydroxide ions are always reciprocally related to each other. The product of their activities, under standard conditions, gives a value 10⁻⁻14. Just watch what happens with the variables when the pH changes, before we continue with the next slide. Here, the various consequences of the lever mechanism are listed. As discussed earlier, the higher the H+ activity in a solution, the lower the activity of OH ions, and vice versa. This implies a consequence, which is quite helpful. Namely, given a specific temperature, the H+ and OH concentrations can be calculated for every pH. The graph below shows an example for pH 5. At this pH, the concentration of H+ can be found where the vertical dashed line crosses the red line. It is therefore 10⁻⁻⁵ mole per liter, or 10 micromole per liter. Meanwhile, the concentration of OH is found at the intersection of the blue line, accordingly, 10⁻⁹ moles per liter, or 1 nanomole per liter. Another exciting aspect of autoprotolysis is that at neutral pH, where the concentrations of both hydronium and hydroxonium ions are equal, their sum reaches a minimum. The low sum of the H+ and the OH concentration, at neutral pH, is the reason for pure water's low conductivity or ionic strength. From there, the ionic strength increases drastically, in either direction, as represented by the dashed B-shaped line in the graph. But which agents can flip that tilt lever? All agents, being able to change the pH of water, namely acids and bases, are called protic agents. Among those protic agents, the acidic ones add hydronium ions, thus lowering the pH. They are called proton donors. Whereas, the alkaline agents remove hydronium ions, hereby shifting the pH to higher values. These agents are called proton acceptors. Acidic compounds add hydronium ions to an aqueous solution. Named after the first person to describe this process scientifically, these proton donors are called Bronsted acids. There are some very well-known agents among the compounds that release H+ ions by dissociation in water as listed here. Let's have a look at each one of them. One of the best-known acid is hydrochloric acid, that is HCl. HCl is a proton donor, which fully dissolves in water, to form a negatively charged chloride anion and a positively charged hydronium ion. Next, we look at the sulfuric acid that is H2SO4. It is one of the strongest inorganic acids and dissociates in a two-stage process, thus forming one sulfate anion with a double negative charge, and two positively charged hydronium ions. Acetic acid is another proton donor. In contrast to the previous acids, it is a weak acid and partly dissociates in water. The resulting chemical equilibrium is symbolized by bidirectional arrows. This also means that under equilibrium conditions the acetic acid, as well as the acetate anion, are always present in the water in a certain quantity. When CO2 dissolves in water, a water molecule combines with carbon dioxide to form carbonic acid. The carbonic acid is shown here together with two water molecules. Because in water the acid turns into hydrogen carbonate by releasing a hydronium ion. The hydrogen carbonate itself can further dissociate to carbonate by releasing a second H+ ion into the liquid. Both reactions are reversible so that at equilibrium all the shown forms can be present in the solution, although in various proportions. This process is not only responsible for the tart flavor of sparkling water, but also for the corrosion of iron in concrete or tubing, and the acidification of the oceans, as a result of the ongoing increase of CO2 in the atmosphere. Now, let us have a closer look at the alkaline compounds, commonly called bases. Which reagents change the solution to alkaline by acting as proton acceptors, that remove H+ from water? As the name alkaline suggests, a prominent group of reagents, that act as proton acceptors are the hydroxide salts of alkaline metals, and alkaline earth metals, such as lithium, sodium, potassium, magnesium, calcium, and barium. The names of the said salts accordingly are lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, and so on. Most of them easily dissolve in water by full dissociation, and are therefore strong bases. But there are also a large number of salts of oxides, and substances of organic origin, which act as bases. The most prominent substance representing the hydroxide salts of alkaline metals is the sodium hydroxide. Sodium hydroxide is a salt that dissolves in water forming Na+ and OH- ions. The latter combines with the next hydronium ions, resulting in the removal of one H+ by forming two water molecules per sodium ion. This process is fast and complete. That's why sodium hydroxide is a strong base and a preferred reagent for titration. Next, we have ammonia. Ammonia is another Bronsted base. With its free electron pair, it acts as a proton acceptor. Ammonia in water accepts a proton from the hydronium ion. It thus turns itself into a positively charged ammonium ion. This happens in an analogous way to water. As with the acids, the process is fully reversible. Therefore, the reaction is written with back and forth arrows. Barium hydroxide is another alkaline salt that acts as a base. It removes two hydronium ions at once, in a rapid and complete step. That makes barium hydroxide a divalent strong base. The result of the reaction is one double-charged solvated barium ion, and four water molecules. Lastly, with phosphate, we complete introducing the concept of Bronsted acids and bases. The interesting thing with phosphate is that it is a weak trivalent base. One phosphate molecule is able to remove three hydronium ions from water. This happens in a three-step process, which is fully reversible. Watch how phosphate acts in the water. This way, phosphate can stabilize the pH in a wide pH range, which makes it a favorite buffer for biochemical applications. The effect of pH buffering will be shown further below. In 1923, the two scientists, Bronsted and Lowry, first expressed a general definition for acid-base reactions in water. They defined an acid as a reactant that provides hydronium ions, also known as a proton donor. The base, the chemical counterpart, that receives hydronium ions, was named proton acceptor. The chemical equation on this page describes a general acid-base equilibrium, where one acid and one base exchange a hydronium ion, Hereby, the acid turns into a so-called conjugate base, and the base into a conjugate acid, respectively. Apart from this theory, other theories, such as Lewis's acid-base theory and a few more, exist which can be read through chemistry textbooks. The particular characteristics of an acid-base reaction, described by Lowry and Bronsted, are as follows. All acid-base reactions are equilibrium reactions, where H+ ions interchange steadily in solution. The equilibrium is reached very fast. In this reaction, every acid has its conjugate base, and every base its conjugate acid. But even at a stable pH value, this dynamic exchange continues, albeit unnoticed. For the purpose of better understanding of the acid-base reactions, two expressions that describe inverse processes are now to be introduced. For this, let's observe a pair of agents. An acidic, represented by formic acid, and an alkaline one, represented by hydrosulfide, example is sodium hydrosulfide. Once combined in water, a transfer of a proton from the acid to the base takes place. This transfer can be broken down into two steps. The deprotonation of an acid describes the removal of an H+ ion from a substance. And the protonation of the base stands for the binding of an H+ ion to an atom or molecule, whereas now you have all the linguistic tools in hand to describe the elementary processes involved in an acid-base reaction. An acid is converted into its conjugate base by deprotonation. Meanwhile, the base is converted into its conjugate acid by protonation. This exchange happens in a dynamic and fully reversible equilibrium process where all four constituents are present in the solution. Only the ability of the individual reactants to bind or release a proton determines the concentration of the relative component. Phew! Was that complicated? Strong acids fully dissociate in water, as exemplified by means of HCl in the animation below. For each HCl added to the water, an equivalent amount of H+ and a Cl- ion are generated, post-dissociation. This results in the lowering of pH toward the acidic region. With strong acids, the pH can be lowered to reach even negative pH units. Same works with strong bases where pH can rise beyond 14. Weak acids behave a bit differently. When a weak acid, or base, is added to water, the pH first changes rapidly to approach a particular value. Eventually, the pH changes slowly, coming to a halt. This happens due to complete dissociation taking place initially, which eventually comes to a halt through partial dissociation. We try to visualize this here by employing our arrow. When a strong acid is added to an aqueous solution of a weak acid, represented here by RH, the weak acid first absorbs the attack of protons, until all molecules of the weak acid are protonated. This effect becomes visible when the change in pH is observed, with the continuous addition of strong acid. The pH change is slowed down significantly, in a range that is shown here on the top of the graphic, using the green lines close to each other. The phenomenon described in the last slide is called buffering of pH, and the range, where the pH is stabilized, is called the buffering range. For a proper visualization of the buffering range, let's rewind the film to the point where the weak acid prevails in its deprotonated form, which is also called the conjugate base, as we already learned. Now, a strong acid is added again to the solution. For the sake of clarity, only the relevant compounds are now shown in the animation. As expected, the pH changes rapidly at the beginning. The pH at which 10% of the weak acid is protonated, the pH change begins to visibly stagnate. Here, we set a marker to indicate the upper limit of the buffering range. From now on, the pH change is delayed considerably, despite further addition of strong acid, until half of the weak acid is protonated. We have now reached the middle of the buffering range. Next, the addition of strong acid is stopped where 90% of the acid is protonated. This is the lower limit of the buffering range. From now on, the solution can be considered as not buffered anymore. 3 important points of the buffering range have now been identified: the upper and lower limit of buffering range and the median. According to this, the width of the range is the pH value of the median, plus minus 1 pH unit. Within this range, 80% of the weak acid gets protonated. It was also shown that the buffering is not constant over the entire buffering range. It decreases on either side of the median until it gets almost insignificant beyond the upper and lower limits. It is of interest to know how strong the buffering is. Buffering capacity, therefore, is a quantitative value used to express the buffering strength of weak acid/base. In other words, it is the measure of resilience against pH change. By nature, the buffering capacity is highest at the median of the buffering range, where there are equal amounts of the protonated and the non-protonated form of the weak acid. The pH of the median is a characteristic value for every product agent and is known as the pKa value of the relevant acid. To either side of the pKa value, the buffering capacity decreases, which is represented in the slide by the intensity of the green color and the blinking arrow. Furthermore, the buffering capacity not only depends on the pH, but also on the concentration of the weak acid. The higher the concentration, the higher the capacity. On this opportunity, let's benefit from the nice graph at hand to show the precise progressions of the concentrations of the acid and its correspondent base with changing pH. The curves are fully reciprocal and intersect at the pKa value. The pKa value not only indicates the pH range where the buffer capacity of a substance is highest, but it is also a powerful measure of the acidity strength of a reagent. The pKa value quasi-represents the weight of a substance in the world of pH. On the top, you see a typical dissociation equilibrium, with Ka as the chemical equilibrium constant. Mathematically spoken, the pKa value is the negative logarithm of this equilibrium constant. In other words, the pKa numerically defines the acidity strength of a substance in water according to the simple rule: the lower the pKa value of a substance, the stronger the acid. The pKa value thus allows us to put every acid in a ranking list. A selection of some product agents from everyday life is shown at the bottom left. It must be noted that, based on known compositions of solutions, pKa values can be used not only for rough pH estimations, but also for precise calculations and predictions of pH. But this is being treated elsewhere. After going through the basic concepts and terminologies of pH, let's explore how pH is measured. At a preliminary level, pH is determined by adding a few drops of a soluble compound, a pH indicator, that changes its color beyond a particular pH value. Each indicator, based on its pKa value, changes color around a narrow pH range, thus confining its applications around it. Hence, a separate indicator would be needed, in a laboratory, in case pH must be analyzed for different range. Next, we have a strip of paper, soaked in a mixture of indicators, which impart different colors for different pH solutions after coming in contact with them. Papers covering the pH range from pH 0 to 14 are called universal pH indicators. Despite the recent advances in these strips, they only offer maximum accuracy of 0.3 pH units. The electrochemical method becomes the most widely accepted method, although more expensive than indicator methods due to its accuracy, online monitoring, and wide measuring pH range. The last two methods are used to measure the pH of primary and secondary standards with high accuracy. Now, let's dive deeply into the components of electrochemical pH measurement with glass electrodes. In fact, this measuring principle is based on two electrodes. The measuring electrode features an H+ sensitive membrane glass at its tip and the reference half cell, providing a well-defined constant electrochemical potential. A pH meter joined up in a circuit between the two electrodes, measures the difference between the potentials, and transforms the voltage into a pH value. For almost 100 years, this measuring principle has been the most common way to determine pH values. The glass electrode at the left is also called measuring half cell, because it only gives a pH value when in use together with a reference half cell. A closer inspection reveals three visible parts: a head acting as handle and connector, a glass shaft housing the inner buffer as well as a guiding element for the electrode signal, and a tip consisting of the particular pH-sensitive glass. For the sake of better visualization, the dimensions of the magnified projection at the right are not shown proportionally. But the indications of size bring the reality to light. The membrane is kind of an ampulla, made of 0.2 to half a millimeter thin glass enclosing the inner buffer. The glass is coated on either side with an ultra-slim gel layer, marked in orange. Whereas the inner layer is exposed to the inner buffer, the outer layer is in direct contact with the sample. These gel layers are 0.1 micrometers thick porous coatings of a negatively charged glass that binds H+ ions highly selectively. In other words, the gels behave indifferently to all other substances that might occur in the sample, except H+ ions. This is the secret of the pH sensor. The production of this type of glass is another secret that manufacturers safely keep to themselves. Imagine now the unrealistic situation of a pH-sensitive electrode tip exposed to two different types of samples, an acidic sample on the left and a basic one on the right. What is the difference between the two situations? In the acidic solution, the supply of H+ ions to bind to the negatively charged outer gel layer is high. Hence, the outer layer gets positively charged. Whereas, in the basic solution, there is very little supply of H+ ions, which drives the remaining H+ ions to leave the gel layer. Hence, the outer layer gets negatively charged. Regardless of the supply of H+ ions in the sample, the pH of the inner buffer remains the same. But the presence of H+ ions in the inner gel layer changes to compensate for the change of positive charge in the outer layer. This slide shows a more dynamic view of the processes at the inner and outer gel of a glass electrode that is immersed in an acidic sample. High supply of H+ ions leads to increased binding of protons to the outer gel layer. The resulting excess of positive charge in the outer layer displaces mobile lithium ions in the vitreous body, thereby transmitting the signal to the inner gel layer. As a consequence, the H+ ions in the inner gel layer are repelled into the inner buffer, creating an excess of positive charge. Due to the high concentration of electrolytes in the inner buffer, the electric impulse is immediately transmitted to the guiding element in the sensor. Similarly, in case of alkaline solutions, low supply of H+ ions leads to protons leaving the gel layer, and hence a negative polarization of the outer membrane. The signal transfer is done by mobile lithium ions in the glass body. This allows H+ ions to bind to the inner gel layer. This results in a lack of positive charge in the inner buffer. The electric impulse is transmitted via the inner buffer to the guiding element in the sensor. When lowering the pH, the measured potential shifts to positive millivolt values. This reciprocal relationship might be confusing. Maybe the following correlations and animations make things easier to keep in mind. Watch how the millivolt signal changes with different pH values. Increasing acidity or more H+ ions result in higher potential, but in lower pH. Also, here, it might be easier to memorize the correlation as follows. Decreasing acidity or less H+ ions result in lower potential, but in higher pH. If one tries to reproduce the shown values with one's own pH meter, sensor, and buffers, one will probably face somewhat different millivolt values. This results from normal deviations of sensor signals from the theoretical values. The visible parts of the reference half cell are a head acting as handle, a connector, and A glass shaft, which is rounded off at the bottom. The glass shaft houses the reference buffer, which can be filled in, and removed, through a filling hole at the top of the shaft. In the photograph at hand, the filling hole is covered by a blue lock, which prevents the leaking of the reference buffer during transport and storage. Inside the buffer, a guiding element, with a particular cartridge can be seen. The function of the latter will be described later on. The function of the reference electrode is to provide a stable potential, to which the potential of the measuring half cell can then be referred. The reference electrode potential thus acts as a 0 point, like the sea level in the determination of geographical height. For this, 4 things are important. A guiding element leading the signal to the meter. A reference element, consisting of a redox system, which provides a well-defined potential. In pH measurement, this is usually a silver-silver chloride system. A concentrated electrolyte solution, which guides the electronic signal quickly through the liquid. The most commonly used electrolyte in pH measurement is 3 molar potassium chloride that is saturated with silver ions. And then, an open junction, which allows an exchange of dissolved ions from the electrolyte with the sample for charge compensation. The junction can be a porous diaphragm, a hole, or a sleeve. The junction is one of the most delicate part of the pH sensor. In particular, when samples contain proteins, amines, sulfides, chlorides, or tris buffer, insoluble complexes with silver can occur and block the junction. Needless to say, that the porous diaphragm is the most susceptible to those blockages. With the Argentol system, METTLER TOLEDO has found an elegant way to overcome the problem of silver precipitates at the junction. This is achieved by encapsulating the Ag+ AgCl redox system in a cartridge. The capsule is filled with glass wool and equipped with a frit. This way, water, and K+, as well as Cl- ions of the reference electrolyte, still have access to the AgCl system. Meanwhile, the undissolved silver chloride remains safely trapped in the cartridge. But what about the dissolved silver ions? They can pass through the glass wool and the frit too, can't they? So an additional appliance is needed. The problem is solved as follows. The silver ions are trapped by a barium chloride layer placed underneath the glass wool. Another porous frit then prevents the barium chloride from being washed out to the reference electrolyte. Thanks to this technology, we are free of any silver ions entering the reference electrolyte. This measure drastically reduces the risk of diaphragm blockage. As the technology evolved, the need to use multiple sensors was eliminated by the introduction of combined sensors. The measuring half cell was integrated concentrically into the reference half cell. For this, the measuring sensor needed a leaner design. Then, the task was to assort the parts of the reference half cell around the measuring half cell to finally get a combined or 2-in-1 pH sensor. The first combined sensor was introduced by Dr. Ingold in 1948. Let's continue the explanations of the measuring principle of pH sensors and concentrate on the pH meter, which receives and processes the data from the electrodes. The pH meter converts the millivolt signal received from the sensor into the corresponding pH value, with the help of the Nernst equation and the values for 3 variables. The first variable, delta E, is the potential measured with the measuring half cell. The second, E0, is the known potential of the reference half cell. And the third, is the temperature in degree Kelvin, which can be entered manually into the meter or by means of a built-in temperature sensor, that is modern 3-in-1 combined sensors. There are now 3 factors remaining in the equation, -2.3, R, the universal gas constant, and F, the Faraday constant. As R and F are constants, their product yield a value of -0.1984 mV per pH in Kelvin. This value, once programmed into the meter, can be used for all further calculations. Most of the pH measurements are performed under laboratory conditions. That's why 25 degrees Celsius, 298.15 degrees Kelvin, is widely regarded as a reference temperature. So, it makes sense to merge the constant in the yellow field with the reference temperature to obtain a clean factor that applies to all such standard conditions. This factor is called Ners Potential and represents the slope of the correspondent equation. What remains is a simple linear equation where all factors, except the pH value, are measurable or known. At the reference temperature of 25 degrees Celsius, the slope of the equation is minus 59.16 mV per pH. Thus the slope value of minus 59.15 mV means that voltage drops minus 59.15 mV per 1 unit decrease in pH. If the measured potential is applied against the pH, the following graph is obtained. It is a line with the aforementioned slope of minus 59.16 mV per pH. The line crosses the y-axis at 414.12 mV, which corresponds to the potential E0 of the reference half cell at 25 degrees Celsius. The x-axis is crossed at neutral pH 7. This intersection does not change with temperature. Therefore, it is also called an isothermal point. It is the case that pH sensors do not normally behave as ideally as they should. Even brand new sensors can slightly deviate from the theoretical values in slope and offset. And the sensors, by nature, do not improve over the course of their life cycle. Therefore, the individual slopes and offsets of every sensor have to be determined regularly. This procedure is called calibration. The following adjustment process allows the pH meter to correct subsequent measurements for such deviations. Calibration and adjustment is performed by means of pH buffers, featuring a well-defined pH value. The slope determined in this way is given as a percentage, xy, of the theoretical value, whereas the offset is given as the deviation at pH 7 in mV. Furthermore, the values of slope and offset allow for a simple assessment of the quality of the sensor. For practical information regarding calibration, please watch METTLER TOLEDO's free on-demand webinar on how to calibrate a pH meter by scanning the QR code flashing at the bottom of the slide. Hope you enjoyed the session. It is practically impossible to cover the entire topic in such a limited time, and so we recommend referring to these resources for more information on pH.